Hello, everyone. In this lecture, we're going to talk about generative models. And this is a new paradigm of machine learning that we have learned for linear regression or logistic regression. So those models, or more generally, the generalized linear model, they are the descriptive models. Okay. So both are probability models, but the discriminative models care about the probability of the target given input, but the generative models care about the joint probability of both the target and features. So that is the difference. So let's consider still a classification problem. So let's consider a classification problem. Where we have the X is the d-dimensional feature and target is maybe 1 up to k predefined categories, okay? So we know that in discriminative models, I assume my target is a multinomial distribution or categorical distribution where the parameters are some softmax of Wx plus b, okay? That is my model assumption. And when I do maximalized estimation, I'm maximizing the parameters, okay? The parameters is the argmax over theta, P of your target. Okay, so you have many targets, so you have n many samples given x1 up to xn, okay? But I can write it more concisely as the log probability for different samples. Okay, P of Tm given xn with my parameters theta. So this is the maximalized estimation for discriminative models. We consider the conditional probability of your target given the feature, given the input x, okay? So this is MLE training. And for inference, we're doing max a posteriori inference, where my target for new data sample is the argmax over the probability Tn given xn. Okay, sorry. T given x star. Okay, with that estimated parameter. Okay, so this is the map inference. So this is the descriptive models. We should be familiar with these models because we have come across with these models in linear regression, logistic regression, and generalized linear models. They all follow this paradigm. But today we're going to talk about the generative model. For a generative model, we care about the joint probability of T and X. So that's why I would suggest MLE is the product. The joint probability of X and T for a data sample and for different samples, okay? Parameterized by theta. So in this case, you have something to say about the data point X, right? Given the data sample feature, like a cat maybe is 2 meters, okay, you know it's unlikely. But in discriminative model, you don't comment on how likely is your feature, okay? You only care about, given that feature, is that a cat or a dog? But in generative learning, you have a joint distribution over the X and T. But for inference, we still have the max a posteriori inference, because the max a posteriori inference gives you the minimum expected loss, okay? So if you care about the accuracy or the error, then you'd rather pick the category that is most likely given that feature. Okay. And we know that in this case, the probability is the same as I say t given x star times p of x star, right? Because p of x star is a constant. It's the probability of data. Even if it's unlikely, we have to say something about that data sample. So that's a constant given the, in terms of your category. So I can multiply p of x here. Then eventually it gives me the joint probability of tx x star t in the estimate parameter. Okay. So this is the generative model. The main difference is in generative model, we care about the joint probability, but in discriminative model, we care about the conditional probability of your target given input, okay? And then during prediction, we will still use the max posteriori inference, but it turns out that it's the same to maximize the joint probability of your target and data x, okay? So the question now becomes, how can I model the joint probability of x and t? Okay, how can I model the joint probability of x and t? So let's consider still our good old example. I have the weight of an animal, and I have a size of an animal, and I have two categories. One is the cat, okay, and the other is the dog. So I know this is a cat, I know these are dogs, okay? So this is cat and this is dog. And I would like to model the joint probability of feature x1, x2, which is the weight and size, as well as the category cat or dog. Okay. So I have two attempts. The first attempt is I first generate xt. I first generate the target t. Then given that target, I would generate x. Okay. So this gives me the joint probability of x and t. And my second attempt is I use the other way of factorization. I first generate x, and given that x, I generate t. Okay, so both are valid probability factorization because of the chain rule. But the question is, which is the more meaningful way of doing the generative model? So I would suggest the first choice, the attempt one here, is the better approach for a few reasons. First, P of x given t is easier to model than P of t given x. Sorry, P of x in general. So the modular probability of P of x, right? Because P of x given t is the probability of your features given that category. So if I know the animal is cat, okay, it may be a Gaussian. If I know the animal is a dog, it's another Gaussian, right? It's another Gaussian. So given cat and P of tx given dog, they are easy to model. But if I model the marginal probability of x, then it gives you a mixture of Gaussian, okay? So this distribution is a little bit harder to model than a single distribution, a single Gaussian, because it's no longer a Gaussian, right? So this is the first reason. And this is actually the main reason. But the second reason is that if I model P of x comma t in this way, then what happens? In the inference time, you argmax over the joint probability of x and t, but you don't have a joint probability of x and t. So you can factorize your probability in this way, then t given x times p of x, because that is your model assumption. Then you can eliminate p of x because it's a constant in terms of your t. Then it reduces to the discriminative model, p of t given x, right? Because here when you do inference, this is a constant during inference. Okay, and this is the discriminative model. Okay, so this shows attempt to degenerates to a discriminative model for classification. Okay, so that's why we typically adopt the first attempt. We first generate the label, and then we generate X given that label. Okay. So the model here is assume that we have T given T is sampled from a multinomial distribution or a categorical distribution from pi1 up to pi k. Okay, those are the class category. So it says maybe half of the samples come from first category, and what is the percentage of the samples come from the second category, so on and so forth. And given T equals K, I have a distribution over X, okay, given T equals K. For different categories, I have a different distribution. If you have a cat, I have a Gaussian here. If you have a dog, I have a Gaussian there, okay? Given a different category, I have a different distribution. But each of the small distributions should be simpler to model than the marginal distribution of X, which gives you a mixture of Gaussian actually. Okay. So this is the assumption for the model assumption for the generative model. Another thing we should be careful about is in generative model, it really depends on what is your X, right? Because now you have a probabilistic assumption of X, but the real vector feature could be very different from a binary indicator. So in discriminative models, we say nothing about X. We only care about T. So it works for both categorical X or for the, for the real valued features, right? I can say this is the size or this is the weight. But I can also say whether the animal is healthy or what kind of subspecies the animal is, okay? But in generative models, we have some assumptions. Given that T, how do you generate X, okay? So we must distinguish between the real valued features or the categorical features, or in fact, you have to make a reasonable assumption of the distribution of your X. So let's consider Gaussian continuous features. Suppose, given a category, my features are Gaussian. And this is a reasonable assumption in this example, right? You want to predict the cat or dog based on the weight and size. So given the cat, the features are somehow Gaussian, right? Given a dog, it's also somehow Gaussian. So it's a reasonable assumption. Then we can flesh out this assumption. So how can I generate the data? So I can specify what is the distribution of X given that T. So I would say, for any data sample, okay. So I first generate Tm from multinomial distribution pi1 up to pi k, okay? So pi's are my parameters. Then given Tm equals k, okay? Suppose I generate my target for the m data sample as k, then my X is sampled from a Gaussian distribution where the mean is the mu k, okay, for the kth Gaussian, and the covariance matrix is sigma k for the kth Gaussian, okay? So this is my assumption of Gaussian continuous features, right? So it says for any data sample, I first pick the category, And then given that category, I generate feature. Okay. In this way, I can sample. Suppose all the parameters are learned, then I can generate more and more data samples, right? I can generate, I can sample different categories and sample different features. Then I can have more and more data points. Okay. So that is also the merit of generative models. So this is the generation story, or the generation story. And this is the key difference between a generative model and a discriminative model. So in discriminative model, you have nothing to say about X, okay? So it says, given X, what is the target? But now the generative says, I know how to generate X, but X is generated in such a way that I first generate a category, and based on the category, I generate X. You have a story, you can sample more and more data points. That is the generative model, okay? Then suppose we are given a data set which is xm, tm, where m from 1 to m as the training set. What is the learning procedure? The learning procedure would be maximalized summation. Okay, so I can write it out. The log likelihood of my data parameterized by theta. Okay, so what are the theta? What are my parameters? Parameters theta are pi 1 up to pi k, as well as mu k, sigma k, okay, for different case. So I can say mu 1, sigma 1, up to mu k, sigma k, okay? These are my parameters. So I would maximize the log likelihood of my data set. And this is the summation over the log likelihood of each data point, okay? And in generative models, I mentioned that it's the joint distribution of the data feature as well as the target with that theta. Okay, and I know that this is the PTM times P of X M given that's Tm. Okay, and my parameters are omitted. Okay, but I can write it out. So I say the parameters here are the pi. Okay, and the parameters here are the mu and sigmas, but I have a set of mu and sigmas. Okay, and the log comes here. So I can factorize this as plus, okay, because it's log product of samples, then I can say it's a plus. Then the okay, I rearrange this term. Oh, okay, I just write one more step. I just write okay. I can introduce another summation saying my little k equals 1 to capital K, then an indicator function saying whether my target is indeed that k, okay? I have an indicator function times the probability, which is a Gaussian, of xm with that mu k and sigma k. right? Then I can change the summation, the term. So I can change the order of the summation. There's no difference, okay? So in such factorization, it turns out that the parameter estimation for the Gaussian generative model here, it decomposes into the small probabilities, right? So here it's a parameter. So here it's a, this bracket only involves pi, okay? It doesn't involve any other parameters. And with each of the summation of k, the probability only involves the parameters mu k and sigma k. It doesn't involve pi. It doesn't involve other things, okay? So this is a little derivation showing that the likelihood decomposes, like log likelihood decomposes, okay? And now when you do argmax over the log of probability, you can do argmax over each term, right? You can do argmax over each term because it's similar to say I have a function f of x, which is x minus 2 squared plus y minus 3 squared, okay, something like this. Then if you want to argmean of this term, you can take the argmean for the first term with respect to x and argmean with the second term with respect to y. You can optimize every term by itself because the parameters decomposes, okay. Then I would give you the result. So pi k is okay. So the maximalized estimation for a multinomial distribution or for a categorical distribution is just counting. So it's just counting the fraction. How likely is your target in that category, okay? If you have the 30% of the target being 1, then you say pi 1 is 30%, okay? This is just counting. And mu k is what I suggest as mk. Right? So this is the maximalized estimation for the Gaussian, where the mu, the mean, is the sample average, okay? So I only care about the samples in that category for this mu, okay? Then, I take the average, and the sigma k is similar. Where mk is the number of samples for that category. Oh, I lost the indicator function. Okay, so basically it says, the class prior, the class probability is just the counting of the fraction of different categories. And then the mean of the category cat is the average, is the average that you consider all the samples that are indeed cat, okay? And the class average of the dog is you consider the samples that are indeed dogs, okay? And similarly, the standard deviation is the x minus mu times x minus mu. So why this happens? This is the reason is the exponential family, the maximalized summation is the moment matching. Okay. So both cases, they are exponential family, and then the maximalized summation is you just match the moment. but I would give another proof for this part. So this is very important because in machine learning, usually we deal with a lot of categorical variables. And it's very important to know that the maximum likelihood estimation for multinomial distribution, for categorical distribution is counting the fraction. Okay, this is a very important result. And let's prove it without using this result. So this is a little bit tricky here because here we have a constraint. We actually have a constraint such that pi1 plus pi2 plus pi k equals 1, okay? And also pi I is greater than or equal to 0 for any I from 1 up to k. So we have some constraints. And if you directly derive the likelihood and you take the derivative and set it to 0, it doesn't give you correct result, because in that case, you can say all the pi's are infinity, then the probability is higher. But in fact, it violates the constraint because it's not a valid probability distribution, okay? So there's some subtlety here, and we're going to do it without using the result. So I'm writing the probability of my log likelihood, okay, T given pi1 up to pi k. So what is the log likelihood of my multinomial distribution? It's actually pi1 to the power of whether my sample is indeed 1 times pi2 to the power of whether my sample is indeed 2, so on and so forth, until pi k to the power of my sample is indeed k, okay? I have the log here. So now I can say the summation over 1 up to m, whether my target is indeed 1 times log of pi1, okay? But I can say I consider not only one category, but also all categories k, then I have another summation for k's, okay? So my maximum summation is to maximize this term subject to these constraints, okay? So the goal is to maximize okay, in terms of my pi's, okay, pi1 up to pi capital K, subject to pi I is greater than or equal to 0, and pi1 plus pi k is 1, okay? So this gives me the constraint optimization problem. And we talked about the constraint optimization problem in previous lectures. That was the equivalence between the LP constraint and the LP soft penalty, right? And we have the same thing here. And what I can tell is you can ignore this constraint temporarily. And after you solve this problem, if it turns out that pi I is indeed satisfied, then you are happy, okay? So you can ignore that temporarily, okay? But you still have the linear constraint. That is very important. Otherwise, I would say pi k equals infinity, then this term is infinity, but it's not a distribution. Okay, so you remember that to solve a constraint optimization, especially it's a convex optimization, we construct the Lagrangian, and then we have the dual problem that gives you the same solution as the primal problem. And to solve that dual problem, you would consider the partial derivative with respect to the primal parameters, as well as the partial derivative with respect to the dual parameters, and you set both to 0, okay? So I consider the Lagrangian, which is the Lagrange multiplier. So I would say the Lagrangian is m from 1 to m, k from 1 to k, Tm equals k times log of pi k, okay, lambda. Okay, so I mentioned that when you consider the constraint, it must be something equals 0, okay? If you have 1, then it's likely that you make an error. So I must have the linear constraint as something equals to 0. Inequality constraint, something less than or equal to 0, okay? But here we ignore the inequality constraint temporarily. So we say lambda pi 1 up to pi k minus 1 equal to 0, okay? Then the primal problem is maximize this subject to that is the same as I would like to first. Okay, how about this? How about let's say minimize? You know, if you mess up the minimization, maximization less than, greater than, or then you are likely to have a you are likely to mess up everything. So why not let's say this? Okay. Then the primal problem is the same as the dual problem, which is the maximize my Lagrangian. So here my primal parameters are pi's, and my dual parameter is the lambda, a scalar. Okay, I only have one constraint, so it should be the max over lambda and mean over pi. Okay, so I would consider the partial derivative of the Lagrangian with respect to pi. I set it to 0. And I will consider the partial derivative of the Lagrangian with respect to lambda. I also set it to 0, okay? So this gives me partial derivative with respect to pi, okay? So I will consider the partial derivative with respect to a particular pi k, set to 0. This gives me minus 1 up to m. Okay. But I consider a particular k, okay? And the pi k is only involved in the term where you have that k, okay? So I can eliminate this summation, okay, of 1 over pi k, okay? If this k is different from the k here, then the partial derivative is 0, right? So I would say this is the partial derivative of the first term. Then I will take the partial derivative of the second term with respect to pi k. That gives me lambda is 0 plus 0, okay? And if you set the partial derivative of the Lagrangian with respect to lambda to 0, then it gives me the primal feasibility. So it gives me pi 1 up to pi k is 1, okay? Then this is first term and this is the second term. So I can represent my lambda. Eventually, I want to eliminate lambda, right? So I can represent my pi k as one over lambda, sum over 1 up to m, indicator function whether my target is indeed k. Okay, this is my pi k. Right? So I would say this is the same thing as here. Then pi k is 1 over lambda, so I think it's correct. So 1 implies, okay? And put 3 into 2. So I have computed pi k in terms of lambda, and I know one constraint of pi k, so I put everything there, and it gives me 1 over lambda summation over different k's, the summation over different n. Okay, and it equals 1. And what is this term? This term tells you, for different k's, and you count how many samples is in that k. And I know that for every sample, it must be one of the category. So this just gives me the number of data samples, which is capital N. So this shows that lambda is capital N, okay, the number of samples. So this implies then you put 4 into 3. Okay, so you have the pi k is 1 over m. So this is exactly the moment matching, you just match the empirical moment. And this is not surprising because we're doing math. And if you derive from one path and you derive from the other path, they must be the same. Okay. So this is the proof 2, the second proof. So the first proof is by the moment matching, proof 1. And the second proof is this. And the third proof, you can eliminate the constraint, saying my pi k is 1 over pi 1 minus pi k minus 1, and you plug it into your likelihood, you get the same thing, okay? But that is a little bit more complicated than the Lagrangian. After you solve this problem, you know that pi k must be positive, okay, or non-negative. So the inequality constraint automatically satisfied. So when you ignore that temporarily, it's not a problem. So this is the learning for the Gaussian continuous variable, and this is known as the Gaussian mixture model. Okay, inference. Suppose, my pi's and my mu k and sigma k's are learned, okay? Then what do you have? Then how do you make a prediction? Then the prediction of t, okay, given a new data sample xt would be the t star is the argmax of different kinds of t given x, okay? And it's the probability that pt jointly with x, okay? It's the argmax. And this is the probability of the p of t times p of x given t, okay? So the posterior is proportional to the prior times likelihood. It's not surprising. Okay. And I would suggest, consider two categories. ij, category I is preferred over category J if and only if P of t equals I times P of x given t equals I is greater than or equal to P of J times P of x given t equals J, okay, for data sample x star. So this is actually saying pi I okay. Then I can move this term into the exponential, right? And I compare the exponent. I just ignore the exponential term here. So now when you rearrange the terms, you find that the x, the condition is a quadratic form of x. Okay, it's a quadratic form of x if sigma I and sigma j are different. But it's a linear form of x if sigma I and sigma j are the same. Okay, so this tells us if sigma I is the same as sigma j, it can be either learned, although it's unlikely, because when you learn something, if it's a real number, then it's unlikely that they happen to be the same. It can also be set manually. So I just manually tie these two parameters, okay? I manually set all the sigmas are the same, okay? Then the decision boundary is a line. Decision boundary is linear. If sigma I is not sigma j, then it's quadratic. Okay. So this tells me that let's consider a few categories. Suppose my first category is this, okay? And my second category is this. Okay. And my third category is this. Okay. And suppose the covariance of the orange Gaussian and the purple Gaussian are the same, then the decision boundary for them is here. Okay, the decision boundary is a linear line. Okay, it's a linear line, right? Because the sigmas are the same, then the quadratic term cancels out. But in case they are not the same, then the decision boundary would be a quadratic line. So the decision boundary will be something like this. Okay, it's quadratic. So the derivation shows that if your features are Gaussian, given a category, then I can use the, this is known as the Gaussian discriminant analysis, which is a generative model. We can model the joint probability of your features and your target labels. And then you do the maximalized estimation. It turns out to estimate a bunch of small probabilities by itself. And then we can do the max posteriori inference by maximizing the joint probability comparison. Between the Gaussian discriminative analysis and the logistic regression. because both are classification. Okay. First, one obvious difference is that the Gaussian discriminant analysis allows you to learn a quadratic decision boundary. But logistic regression, if you have the original features, you only have the linear boundary. But that is not the main issue because you can include the quadratic features and it also allows you to learn a quadratic decision boundary. But the main thing is there's some theoretical results. Saying if the data are indeed Gaussian, then this is better, okay, by some theoretical analysis. But this rarely happens in real applications because no real data are indeed Gaussian, okay? In practice, it turns out that we don't use the Gaussian discriminant analysis too often. We typically use the logistic regression, okay? The reason is that suppose you have D features and you extend it by one trivial feature, then the number of parameters in logistic regression is D. Okay, D plus 1 because you have a bias term. But the number of parameters here is, suppose you have K categories, you first have the K minus 1 degree of freedoms for the class prior, right? Then you have the K times D for the mean, okay? And you have the K times D minus 1, K times the covariance matrix, okay? The covariance matrix is the D by D, okay? D squared, but it's symmetric, okay? You have that many parameters in the covariance matrix, but sometimes you can tie the parameters, you can group them here, but still it's way larger than that. So in practice, the Gaussian discriminant analysis is not a very fancy model. We don't use that very often, okay? So by default, you should use the logistic regression. But there's another usage for generative model, which is unsupervised learning, okay? So I have the same model here. Where are we? So I have the same model here, but my training data only contains X, okay? I don't know the labels. In this way, I can still learn a machine learning model by maximalized estimation because in this time, the maximalized estimation of my data, P of data, with some theta would be the log likelihood of P of X with T, joined with T, but we don't know the T, so we can sum over different kinds of T's, okay? So it's still valid, okay? So in the generative model, even if the labels are unobserved, you still know that these data samples are different from those data samples. Although you won't be able to tell this is a cat, that is a dog, because you haven't been trained what is the semantics of a cat or a dog, but you still can separate them apart. But in discriminative learning, this is not valid because the discriminative learning is to model the target given X, but now your target is unobserved. The formulation in discriminative learning is ill-defined, okay? So you cannot do that for unsupervised learning. But in terms of plain classification, everything is observed and the data may not precisely come from a Gaussian distribution, then usually we use the logistic regression, okay? The Gaussian discriminant analysis or the Gaussian mixture model is not very widely used. So this is one example. And the other example, I would say, is called the naive Bayes model for text classification. It's very often used in text classification before the neural networks become the prevailing method. So consider a document. So let's consider a document. You have there are different formulations of naive Bayes, but let's consider one of the formulation, okay? A document contains a lot of words, okay? And then the word, I can extract a word by a bag of word features, okay? Which is the V1, V2, up to VK, whether they occur. So I said this is 0, 0, 1, 1, 0, 0, 1, okay? So this tells you whether the features occur or not in this document. This is the naive Bayes assumption. So this is the bag of words features to represent the document. And these are my input x, okay? X is a vector, which is the k. So I can say this is VD. So it's a D-dimensional space. And I can say my target is still 1 up to k, okay? So for example, 1 is the category of sports news. Second, 2 is the category of the political news, so on and so forth. You have k types of categories, okay? Then the naive Bayes model says, first, I generate T from a multinomial distribution of pi 1 up to pi k. It's the same as the Gaussian discriminant analysis. We first generate the target based on the categorical distribution. But then when we generate data, I cannot generate the data from Gaussian because 0, 1 indicators are definitely not Gaussian. If you approximate it by a Gaussian, it doesn't give you good results. So I would say, why not let's for maybe I from 1 up to D, okay? For every word, I will generate xi from a Bernoulli distribution, okay, indicating what is the chance that this word occurs, okay, with that category. So given T equals K, that is the Bernoulli distribution. I can call it pi for the ith word in that category K, okay? So this pi is different from that pi. So this pi is the distribution of my category of text. And these pi k are the probabilities of whether my word, ith word, would occur or not in the kth category, okay? So this is one formulation. Another formulation, I can say multinomial distribution, pi 1 up to pi k. For suppose I have n words in this document. This is the W1, W2 up to Wn, okay, n words. Another formulation is for I equals 1 up to n, and I will generate my Wi for different words, given that T from K from a multinomial distribution over my vocabulary, okay? So my vocabulary, which is up to K vocabulary, okay? So it says, I first generate the category, then if I know the category, what is the chance that my first word is W1? What is the chance that my second word is W2, okay? So these are two different formulations for naive Bayes. And why is it called naive Bayes? The naive here indicates different words are independent, okay? So it says, if I generate V1 is 0, it's independent of whether my V2 is 0 or 1, and independent of V3, V4, so on and so forth, okay? It's the independent assumption. And for multinomial case, it's the same. So I would generate my words, first word and second word, so on and so forth, independently. And that is definitely not true, right? In real natural language, usually the previous word would affect your future word. But in the naive Bayes assumption, we assume every word is generated independently. And we can do a generative model to estimate the joint probability of your target as well as your document, okay? And the parameter estimation for this should be simple. It's just the counting. It's the same as estimating the categorical distribution for the Gaussian discriminant analysis. It's just counting, and the details are omitted. I don't want to present it here now. Okay, that's it for this lecture. See you next time.